So having calculated an ionic strength of solution, how does ionic strength impact what we know about chemical equilibrium? Well, it turns out that ionic strength is used to calculate values to modify the way we write equilibrium constants traditionally by replacing chemical concentrations, a related but more accurate statement of chemical concentration known as chemical activities. So remember, typically for a generic reaction, A moles of A plus B moles of B are in equilibrium with C moles of C and D moles of D. We would write an equilibrium constant as products over reactants, every species concentration or partial pressure raised to their stoichiometric coefficients. Since ionic strength generally only applies to chemical reactions that are taking place in water, we're going to assume that this equilibrium constant is primarily a concentration-based equilibrium constant. And our numerator is concentration of C to the C times concentration of D to the D, divided by concentration of A to the A, and concentration of B to the B. This is the form of the equilibrium constant that you've always been taught in general chemistry, or most people are always taught in general chemistry. But this form of the equilibrium constant is only a good quantitative approximation of chemicals' equilibrium behavior if the ionic strength of solution is zero. If your ionic strength of solution is higher than zero, then there's a better way to write an equilibrium constant expression that accounts for ionic strength, which is known as an equilibrium constant expression in terms of what we call chemical activities. So chemical activities are, from a physics or a physical chemistry perspective, a more accurate way to write an equilibrium constant expression to begin with. And every chemical dissolved in a solvent, particularly water, or participating in a chemical reaction, can be said to have a chemical activity. You can think about an activity as essentially a chemical concentration in this class, but that concentration is modified by a special term called an activity coefficient, where the job of the activity coefficient is to take the ionic strength of solution into account in terms of how the behavior of this chemical is going to be affected by the presence of other ions around it. So if you were to write the activity of a chemical species C, you would write capital A lowercase c, that would be the activity of chemical species C, is equal to the concentration of chemical C times the activity coefficient for C at a specific ionic strength. So bracket C is still concentration of C, whereas gamma sub C is a constant that we call an activity coefficient, which depends on the ionic strength of solution. And so you can think of activities as a more fundamentally correct way to express how the concentration of a chemical impacts the equilibrium state of a chemical reaction. And anytime we write an equilibrium statement, whether that's an equilibrium constant expression or the definition of pH, the strategy is going to be, if we're working in a solution where ionic strength effects matter, where the ionic strength is not zero, we can get a more accurate determination of the chemical's behavior by replacing the concentration of the chemical, like we would use in general chemistry, with the activity of the chemical, the concentration times this activity coefficient. And so what we want to show you first is how we rewrite equilibrium constants in terms of activities, and then we're going to show you how we can calculate the value of these activity coefficients to make better quantitative determinations of the concentrations of various chemicals in any equilibrium system. So what this boils down to is activities are a more fundamentally true and more quantitatively accurate way of measuring the concentration of chemical species in any solution where the ionic strength of solution is not zero. So how do we take these activities into account when we write equilibrium constants? Well, there's not much to change here, except instead of writing equilibrium constants in terms of concentrations, we now write them in terms of activities. So a better way to write any equilibrium constant expression is to write it in terms of activities, not concentrations. In general chemistry, we could get away with writing concentration-based equilibrium constants because we were generally working in solutions that had only a single chemical component and ionic strength effects were negligible. But in this class, there are going to be specific situations, but it's not a tool we use all the time, where we'll get a more accurate answer as to the concentration of a specific chemical that's part of a chemical equilibrium if we write the equilibrium constant in terms of activities rather than concentrations. So the key words that would lead you to look to write an equilibrium constant in terms of activities are, you see, measurable ionic strength, or non-zero ionic strength, or the ionic strength of solution is this. If you know what the ionic strength of solution is, or you know that it's not zero, you're going to get a better idea of how the chemical system behaves by writing an activity-based equilibrium constant, not a concentration-based equilibrium constant. So now if we look at a chemical reaction, A moles of A plus B moles of B is in equilibrium with C moles of C and D moles of D, I hope that in your mind you'll start to reroute and say the most fundamentally correct way to write this equilibrium constant is not the concentrations of all these species, but the activities of the products divided by the activities of the reactants, still with everything raised to their stoichiometric power. Our generic equilibrium constant becomes the activity of compound C raised to the C times the activity of compound D raised to the D, divided by the activity of compound A to the A times the activity of compound B to the B. And remembering that an activity is defined as the activity coefficient times the concentration, we can reframe that activity-based equilibrium constant in more friendly terms, where we say, okay, well, the activity of compound C is the concentration of compound C to the C power times the activity coefficient of C raised to the C power. The activity of D is the concentration of D to the D power times the activity coefficient of D to the D power, and so on. So now the way we'll write equilibrium coefficients when we have non-zero ionic strengths in solution is to insert next to the concentration terms an activity coefficient term that gets raised to the same power. So this is something we want to practice a little bit here. I think it's going to be something that you get the hang of. But first, I just want to make mention of why it's important that we take these ionic strength effects into account when we're talking about the behavior of chemicals in an aqueous solution. In solution, ions don't actually just exist as ions. They're being ferried around or shepherded around by water molecules, and they're being chased after by other ions that are in solution with opposite charge. So whenever you think of an ion in water, you should think of it as surrounded by this big globule hydration sphere of water and associated ions. And if you're looking at a simple solution like sodium chloride with some other ions around it, the chloride has its own envelope of associated water molecules, this hydration sphere. The sodium has its own envelope of water molecules, which is its hydration sphere. And then any other ions in solution that have an opposite charge are being pulled loosely towards these ions at the center of the hydration sphere by electrostatic attraction. So if you're a negative ion like chloride, you have a bunch of little positively charged cations, could be sodium, could be any other cations that are present in solution, kind of stuck into this surrounding hydration sphere of water molecules, trying to get to this chloride ion. And the opposite for the sodium ion. Bunch of negatively charged anions weakly attracted to the sodium at the center of this hydration sphere. And so when two chemicals undergo a chemical reaction, they have to shed not only this hydration sphere of water, but they also have to shed this weakly bound, electrostatically attracted layer of ions that have opposite charge. And how big this hydration sphere is, and how strongly those other ions are chasing after the ion at the center of the hydration sphere, depends on the charge of the ion and the size of the ion. The higher the charge on the ion and the smaller the ion, the larger its hydration sphere becomes, and the more strongly other ions in solution are pulled towards the ion at the center of the hydration sphere. And so that's what ionic strength and activity coefficients are modeling for us. The effect of trying to do these chemical reactions while recognizing that not only do the two participating species have to run into each other, but they have to shed these hydration spheres if they want to undergo a chemical reaction. The last bit of practice here, I'd like us to practice writing equilibrium constant expressions while keeping ionic strength in mind. We're going to write equilibrium constants for the solubility products of two ionic compounds, lead-2 iodide and lanthanum sulfate. But when writing the equilibrium constant expression, we're going to write them in terms of activities because we're considering the effect of ionic strength. All right, we're going to write equilibrium constants for the solubility product. First and foremost, we have to recognize from our vocabulary that solubility products describe the dissociation, the breaking up of ions that are part of an ionic compound to give you individual ions. So if we're talking about lead-2 iodide, the relevant chemical reaction is PbI2 solid breaks up into 1 mole of lead-2, Pb2+, and 2 moles of I-. So this is the reverse of a precipitation reaction. The KSP in general chemistry we would have written as the concentration of lead-2+ times the concentration of I- squared. But when taking activity coefficients into account, the equilibrium constant expression should be written as the activity of lead-2+ times the activity of iodide squared. Or we can write the activity coefficient of lead-2+ times the concentration of lead-2+ times the activity coefficient of iodide squared times the concentration of iodide squared. Lanthanum sulfate is a compound with a chemical formula that might be a little harder to bring to mind. Lanthanum is a rare earth metal. It's a lanthanide. It's one of those universally radioactive isotope F block elements. And so it's not one that we think about a lot. So one thing that I didn't tell you in this problem, and I wouldn't necessarily expect you to know, which is why I'm giving you the hint here, is most of your F block elements uniformly form +3 cations. So if you see lanthanum sulfate, the charge on that lanthanum is almost certainly going to be +3. The charge on sulfate is -2. Therefore, the chemical formula of lanthanum sulfate is La2SO4 in parentheses 3. That breaks apart in water to form 2 moles of lanthanum 3+ and 3 moles of sulfate. Solid dissociates to give you these species. The KSP we would have traditionally written as the lanthanum concentration squared times the sulfate concentration cubed, but now considering ionic strength effects, we replace those concentration terms with activities, and keeping in mind that the activity is the activity coefficient times the concentration, this leads us to a KSP when we need to consider ionic strength effects of the activity coefficient for lanthanum squared times the concentration of the lanthanum ion squared times the activity coefficient for sulfate cubed times the concentration of sulfate cubed. And so recognize this is not a big change, but it's a mathematically significant change that when we have ionic strength effects to worry about, we have to start writing our KSP expressions with the activity coefficients raised to the same power as the concentration. And that's going to be our first new tool in solving equilibrium problems. In our next lecture segment, we're going to talk about how we can use equations or tables to determine the value of these activity coefficients, gamma, and then we'll show you how to start using them to solve equilibrium problems more accurately. So I'll see you there.